A variable frequency drive, or VFD, can indeed enable a fan motor to continue operating even when the voltage is reduced. VFD have the capability to adjust both the frequency and the voltage that is supplied to the motor. This adjustment allows the motor to operate at lower speeds without experiencing a dropout due to a thermal overload condition. Now, regarding the question of whether a drive can start a motor during an undervoltage condition, the answer depends on the specific VFD unit itself. While some VFD are designed with the ability to initiate motor starts even when the voltage is below the standard level, it's not a universal feature across all models. Several factors come into play when determining whether a VFD can successfully start a motor under such conditions. Firstly, there's the VFD inherent starting torque capability. Secondly, the full load current that the motor requires is crucial. And thirdly, the available line voltage at the time of starting needs to be taken into account. All these elements interact to determine the feasibility of an undervoltage start. Now let's consider some additional aspects to understand the implications of operating a motor with a VFD under reduced voltage. The motor speed will be directly affected. Specifically, the motor will operate at a lower speed than its normal rated speed. This reduction in speed is proportional to the extent of the voltage reduction. So, if the voltage is significantly lower, expect a correspondingly low motor speed. In addition to the speed, the motor's torque output will also be impacted. The torque, which is the rotational force that the motor can exert, will be reduced due to the low voltage. This decrease in torque can have practical consequences, particularly for applications like fans where consistent performance is needed. If the torque is insufficient, the fan's performance may suffer. Therefore, when considering a VFD solution, proper selection is paramount. Choosing a VFD with voltage and current ratings that are appropriate for the motor is crucial to ensure compatibility and reliable operation. The VFD should be capable of handling the motor's specific electrical requirements, even under reduced voltage conditions. Now let's recap the overall benefits that installing a VFD in place of a across-the-line controller can provide. Firstly, the VFD allows continued operation of the motor even when the voltage is reduced below its normal level. This ensures that essential functions, such as fan operation, can continue uninterrupted. Secondly, VFD offer precise speed control. This allows operators to adjust the motor's speed to match the specific demands of the application, providing flexibility and efficiency. Thirdly, there are potential energy savings. By adjusting the motor speed to align with the actual requirements, the VFD can reduce energy consumption, leading to cost savings and environmental benefits. Fourthly, VFD often come equipped with additional protection features. These features may include overvoltage protection and overcurrent protection, safeguarding the motor and the system from electrical faults. In summary, a VFD offers a comprehensive solution for managing motor operation, particularly in situations where voltage fluctuations or reduced voltage conditions are concerned. It provides operational continuity, precise control, potential energy savings, and valuable protection features. Understanding these benefits and selecting the right VFD for the application can lead to significant improvements in system performance and reliability. In the specific case of a 30 horsepower, 208 volt, 3-phase motor experiencing thermal overload conditions due to reduced voltage from the power company, replacing the across-the-line controller with a VFD is a viable solution. The VFD ability to adjust frequency and voltage allows the motor to operate at lower speeds without dropping out, even with an input voltage of around 190 volts. To further elaborate on the operational aspects and considerations when using a VFD in such a scenario, let's delve into some key areas. First, understanding how VFD work to mitigate undervoltage issues is essential. A VFD essentially converts the incoming AC power into DC power and then inverts it back into AC power, but with adjustable frequency and voltage. This conversion process allows the VFD to maintain a relatively stable voltage and frequency supply to the motor, even if the incoming voltage fluctuates. When the incoming voltage drops, the VFD can compensate by drawing more current to maintain the required power output to the motor. However, there are limits to this compensation, which we'll discuss further. Secondly, starting capability under voltage is a critical factor. As mentioned earlier, not all VFD can start a motor under voltage conditions. The ability to do so depends on the VFD design and its built-in protection features. Some VFD have undervoltage protection that will prevent them from starting if the input voltage is below a certain threshold to protect the VFD itself and the motor. Others have a ride-through feature that allows them to continue operating for a short period during voltage dips. For starting under voltage, it's crucial to select a VFD specifically designed for this capability, often referred to as having enhanced undervoltage tolerance or a robust starting torque feature. Thirdly, let's discuss the impact on motor speed and torque. When the VFD operates the motor at a lower voltage, the motor's speed will be reduced. The relationship between voltage and speed is generally linear, so a significant voltage drop will result in a proportional decrease in speed. Additionally, the motor's torque will also be affected. Torque is proportional to the square of the voltage, so a small decrease in voltage can lead to a more significant reduction in torque. This is particularly important for fan applications, as the fan's airflow is directly related to its speed and torque. If the torque is insufficient, the fan may not be able to provide the required airflow, leading to performance issues. Fourthly, selecting the right VFD is paramount. Several factors should be considered when choosing a VFD for this application. Firstly, the VFD voltage and current ratings must be compatible with the motor's specifications. The VFD should be able to handle the motor's full load current and have a voltage rating that matches the incoming power supply. Secondly, consider the VFD overload capacity. The VFD should be able to handle occasional overloads without tripping or shutting down. Thirdly, look for a VFD with built-in protection features such as overvoltage protection, overcurrent protection, and undervoltage protection. These features can help protect the motor and the VFD from damage. Fourthly, consider the VFD communication capabilities. Some VFD have built-in communication interfaces that allow them to be integrated into a larger control system. Fifthly, think about the VFD ease of use and programming. A user-friendly interface can make it easier to set up and configure the VFD. Fifthly, let's explore some additional benefits of using a VFD. Firstly, energy savings. VFD can significantly reduce energy consumption by adjusting the motor's speed to match the demand. This is particularly beneficial for fan applications, where the demand often varies depending on the time of day or the season. Secondly, extended motor life. By reducing the stress in the motor, VFD can help extend its lifespan. Thirdly, improved process control. VFD allow for precise control of the motor's speed and torque, which can improve the overall process control. Fourthly, reduce mechanical stress. By starting and stopping the motor smoothly, VFD can reduce mechanical stress in the motor and the connected equipment. In the specific scenario described, where the power company is generating power at a reduced voltage due to network feeder issues, installing a VFD can provide a reliable solution to keep the fan motor running. By carefully selecting the right VFD and configuring it properly, it is possible to mitigate the effects of undervoltage and maintain the required fan performance. However, it is important to be aware of the potential limitations and to monitor the system closely to ensure that it is operating within its safe limits. In addition to the previous points, let's consider some practical aspects of implementing a VFD solution in this specific situation. Firstly, a thorough assessment of the motor and the application is necessary. This includes gathering information about the motor's nameplate data, the fan's performance requirements, and the characteristics of the incoming power supply. Secondly, consult with a qualified electrician or VFD specialist. They can help you select the right VFD for your application and ensure that it is installed and configured properly. Thirdly, ensure proper grounding and wiring. Proper grounding is essential for the safe and reliable operation of the VFD. The wiring should be sized appropriately for the motor's full load current. Fourthly, set the VFD parameters correctly. The VFD parameters should be set according to the motor's nameplate data and the application requirements. This includes setting the motor voltage, current, speed, and torque limits. Fifthly, monitor the VFD performance. Monitor the VFD input voltage, output voltage, current, and frequency. This will help you identify any potential problems early on. Sixthly, consider using a line reactor or DC choke. A line reactor or DC choke can help improve the VFD performance and protect it from voltage transients. Seventhly, provide adequate cooling. VFD generate heat, so it is important to provide adequate cooling to prevent them from overheating. Eighthly, consider using a bypass circuit. A bypass circuit allows you to bypass the VFD and run the motor directly from the power supply in case of a VFD failure. Ninthly, train personnel on the VFD operation and maintenance. Proper training is essential for ensuring the safe and reliable operation of the VFD. Tenthly, implement a regular maintenance program. A regular maintenance program can help prevent problems and extend the VFD lifespan. Now let's address the potential for energy savings in more detail. A VFD can save energy by adjusting the motor's speed to match the demand. This is particularly beneficial for fan applications, where the demand often varies depending on the time of day, the season, or the occupancy of the building. For example, during periods of low demand, the fan speed can be reduced, saving energy. The amount of energy savings will depend on the specific application and the operating profile. However, in many cases, a VFD can save 20% or more on energy costs. To maximize energy savings, it is important to properly size the VFD and to optimize its control parameters. In addition to energy savings, a VFD can also provide other benefits such as reduced motor wear and tear, improved process control, and reduced noise levels. By starting and stopping the motor smoothly, a VFD can reduce mechanical stress on the motor and the connected equipment. This can extend the motor's lifespan and reduce maintenance costs. A VFD can also provide more precise control of the motor's speed and torque, which can improve the overall process control. Finally, a VFD can reduce noise levels by operating the motor at a lower speed. In conclusion, installing a VFD in place of an across-the-line controller is a viable solution for operating a 30 horsepower, 208 volt, three-phase motor experiencing thermal overload conditions due to reduced voltage from the power company. The VFD ability to adjust frequency and voltage allows the motor to operate at lower speeds without dropping out, even with an input voltage of around 190 volts. By carefully selecting the right VFD, configuring it properly, and implementing our regular maintenance program, it is possible to mitigate the effects of undervoltage, maintain the required fan performance, and achieve significant energy savings. Remember to consult with a qualified electrician or VFD specialist to ensure that the VFD is installed and configured properly. This will help you maximize the benefits of the VFD and ensure its safe and reliable operation. It is also crucial to continually monitor the VFD performance and make adjustments as needed to optimize its operation. A well-implemented VFD solution can provide long-term benefits in terms of energy savings, reduced maintenance costs, and improved process control.